Let's have the final talk here by Katharina Heidler on formalizing the one-way to hiding theorem in Isabelle. Please.
So thanks for staying here. I hope I will give you some intuition. I'm pretty sure that very few of you know what the one-way to hiding theorem is. So I just call the talk as a second title, On the Way to Foundationally Formalizing Quantum Security Proofs. So it's about something about quantum and security proofs. Okay, this is joint work with Dominique Unruh from RWTH Aachen. Okay, so let's just talk a bit about what is this quantum security, why do we care, what is it? So probably you will have heard of the latest news from the quantum world where Google announced last December that they have a new quantum computer called Willow. And it's so much better, and it's one step further to having this kind of large-scale quantum computer. But why do we care? So we care, at least in the cryptography world, we care because with large-scale quantum computers, all widely known crypto systems like RSA, Diffie-Hellman would be broken quite easily. So once these kind of large-scale quantum computers exist, we are just messed up. So there's a lot of efforts going into finding new kinds of crypto systems that are also secure against quantum computers. And this is called the post-quantum cryptography or crypto systems. So maybe you've heard of that. So it's a bit about, it goes in this direction. So let's talk a bit more about what quantum computers can do in comparison to classical computers. So probably you know something about that already. Just have a quick overview. So classically you have bits 0 and 1, but and they are embedded in this kind of quantum world as a computational basis, but a quantum computer, or the smallest entity of the quantum computer is the qubit, and this can do more than just having a 0 or 1 stored. It can have some kind of probability distribution on 0 and 1. So we are talking about distributions of states, and they can have some very interesting properties. For example, one very interesting property is this kind of superposition, which is this kind of distribution over several states. For example, so in this case, if you have alpha times one of the base states and beta times the other base state, then you would require, if this is a probability distribution, that alpha squared and beta squared should be equal to 1. And what you can also have, and this is not entirely correct, like what is stated right here with the entanglement, but what is interesting in quantum computers is also you can have some kind of entanglement between bits, which says that you don't have all the information of distributions in one bit, but it could be somehow connected to something, to another bit. So, for example, there's this kind of entanglement that says if you have that you can entangle two qubits, and whenever you measure one of them, the other one is going to have exactly the same result. So you have some kind of very strange connection going on there. Something else that is notable when talking about this quantum computing is everything is based on this quantum mechanics, and there's a lot of mathematics going on behind there. We are talking about when we calculate stuff in, or when we model a quantum computer, we're talking about Hilbert spaces and vectors over Hilbert spaces and operators over Hilbert spaces. So it goes very deep into mathematics very quickly. Okay, so this is one part, like the quantum part. Let's talk also about the security proofs part. What is a security proof? It's mostly when you have a crypto system and you want to say it's secure about against some attack, for example. There's, for example, the indistinguishability under chosen plaintext attack that you will probably know, which says the adversary can choose two messages and ask you to encrypt one of them, but not knowing which one, and the adversary has to somehow find out which one of the messages it was. So the adversary has to gain some kind of information on the encryption system or on the messages. So overall, quantum security proofs is when we are doing this kind of post-quantum crypto systems classically on our laptops, on our smartphones, wherever. But this should not only be secure when the adversary has powers of huge classical computers, but also has access to quantum computers. So that's the new feature, that these kind of crypto systems should be secure also against attacks using quantum computers. Okay, so what is this one-way to hiding theorem, and where in this huge setting is it placed? So I kind of drew like an overview of what is going on in this whole quantum security world. So of course, in the end, can I see this? No. Okay, never mind. So in the end, we, of course, want some kind of security proofs for concrete crypto systems. For example, there has been released a new standard by the National Institute of Standards and Technology by the US called MLChem, if you know that, based on Kyber. And for example, this is going to be the new standard. We want to show proofs that this is safe and secure to use when attacking with classical and quantum computers. So we want, for example, some security proof for Kyber. Of course, we need a lot of background theory that helps show these proofs. We also need some kind of model of the quantum computer or the quantum adversary. We need to state in these security proofs what can the quantum computer do, how are we modeling it, what can the adversary do, how are we modeling that. And one essential feature of most of these security proofs in cryptography use something called the random oracle model. Maybe you've heard of that already, which is some tool in classical cryptography to somehow handle some reasoning steps in these security proofs. And there's a quantum analogon to that, which is the quantum random oracle model, and that says more or less just, okay, we take a normal classical random oracle model, but we allow quantum access to this kind of classical function. And exactly at this point, that's where the one-way to hiding theorem is coming into place. It's talking about how we can rewrite quantum random oracle models in such a way that we can use these rewriting steps for our security proofs. And then using this one-way to hiding theorem, we will formulate these kind of security game steps within the quantum world. And just for you to know, this one-way to hiding theorem is used in, I think, most of the security proofs for post-quantum crypto systems. So I know for sure for Kyber, for Saber, for dilithium. So it's like one of the central background theorems that are used. So of course, we want to somehow know whether all this formal stuff, all this mathematics, very complicated stuff going on is actually correct, and the reasoning is sound. So we want to formalize this, and in our case, we want to formalize it in Isabelle. So why? There is something called the QRHL tool, which is developed by Dominique, and this gives us a formal tool to verify and formalize this kind of quantum security proofs. So we have this QRHL tool, which is based on Isabelle. So the background libraries are all in Isabelle. So we have to write all the background theory also in Isabelle, we have to model the quantum computer and the quantum adversary also in Isabelle, and we also have this quantum random oracle model in Isabelle, and we have to model how can we formalize like the access of the adversary to this quantum random oracle model. And what we did in our paper here is that we formalized the one-way to hiding theorem in Isabelle and foundationally formalized the proof of this theorem as well. So then the idea would be to show that this formalization of the one-way to hiding theorem can then be used in Isabelle for the game steps, and again be integrated in the QRHL tool to completely be sure about all the foundations used in this tool. Okay, so that's what we're going to do. We still don't really know what this one-way to hiding theorem is actually about, so I thought about giving you a bit of an intuition of this theorem. So what is the intuitive idea behind it is what I like to call reprogramming. So imagine that you have some kind of function, for example, a function given by the random oracle model or something like that. And in a classical way, you would say, okay, the adversary is allowed a finite number of accesses to this kind of random oracle model function. So he can ask for a finite number of function values. And the reprogramming in a classical way says, okay, if we just change the function values in a very small change set, the adversary most likely will not notice. Why? Because he just can ask for a finite number of points, and if we limit like this number of points, and if we constrain the change set, the probability that the adversary will actually ask for something inside the change set is negligibly small. So this is a central reasoning about how to change this kind of random oracle models classically. And the question that we pose now is, what about the quantum random oracle model? So in the quantum setting, we said, okay, we have superpositions, so we can ask for a probability distribution over states. So what about asking in just one query to the quantum random oracle model for a superposition of all states at once? So you somehow get a probability distribution over all function values at one step only. And the question is, if the adversary is allowed to have some kind of probability distributions over sets, over function values as well, can he detect these changes that we want to make? And if yes, with what probability can he detect that? And that's what the one-way to hiding theorem is all about. It gives a bound on the probability that the adversary can find some kind of information gain from changing a small set in this huge random oracle model. So this is just a theorem statement from the paper by Ambainis, Hamburg and Unruh, called Quantum Security Proofs Using Semi-Classical Oracles from 2018. And that's just the theorem statement, and you have like this left and right probabilities which say, okay, one oracle, and then we change the oracle, and then we have the right state oracle. And we can, so in the bottom line here, you see that you can bound the difference between the left and right probabilities by some kind of value that is mostly dependent on the change set. So this is a very nice bound because it does not depend on the oracles themselves anymore, but mostly on the change set only. Okay, and this is what we formalize in Isabelle, and it looks like this. Seems quite pretty, but there's a lot of stuff going on behind the scenes. So, for example, you can see in the assumes here already that there's something called, with trace preserving maps. So we have to really go into the mathematics here about Krauss families this is Krauss maps, some kind of weird function or operators on Hilbert space operators. So there's really hard mathematics going on behind there. But we could formalize this theorem in Isabelle and all the proofs, which of course are left out here because it would just have taken too much space. Okay, so if we dive a bit deeper into our contribution of the formalization, so what did we do? We foundationally formalized the one-way-to-hiding theorem. So for example, in this QRHL tool, there is an axiomatization of the one-way-to-hiding theorem, but there's no proof so far. And as far as I know, there's also no other theorem prover that can handle this kind of formalizations. We did not only formalize, but we also improved the mathematics behind the one-way-to-hiding theorem. So for example, the proof is split into what is called the pure case and the mixed case state. And so the mixed state is a bit more difficult in the quantum world. And we gave a new and easier proof for this kind of mixed state case. This omitted something called Buer's distance and fidelity of quantum states, which I didn't know about. You probably also don't know about it, and would have taken us months to formalize a whole new library about these concepts in quantum information theory. So we decided, let's just change the proof. And we could find a new proof here. And we also generalized two other things. Firstly, the original proof or the original statement was only for finite dimensional Hilbert spaces, and we generalized this to infinite dimensional Hilbert spaces. And the second one is, so far we only had terminating adversaries, and now we also are allowed to have non-terminating adversaries. So we also, since we had a very close connection between the proofs, which are also mostly done by Dominique, and we worked a lot together about formalizing. And I asked, okay, I couldn't formalize this part, what is happening here? And Dominique answered, yeah, let's just try and find a different proof. And so there was a lot of collaboration there, which was really nice. And we got some really cool results out of that. Okay, still, every formalization has their own constraints, and our work also has some constraints. So first of all, we have no parallel quantum queries implemented, so every query to the random oracle model is just one query at a time, no parallel queries. And the reason is a bit that the type of the quantum query would depend on the number of parallel queries. So in Isabelle, it's always a bit hard to have this kind of, somehow find a way to formalize this kind of dependent types. There are some methods like tricks, how you can get around these problems, and this would be needed to finally join our work to the formalization done in QRHL tool. So this is really a step that would be needed in the future. I have some ideas about that, how to do it, but I think it's going to take a bit of work. And second, so the probabilities you saw before, like this P left and P right, they actually are dependent on some distributions on the change set and the oracles and another random input. And up to now, these distributions were discrete. And I'm pretty sure that they can also be extended to arbitrary distributions, but that would lead to even more limit arguments and some more, you have to be a bit careful about everything. So I think this is possible, but it would also take quite some work to do this. So if you're interested in this work, there's a link to our formalization, and we're planning to submit this to the AFP. There's still some dependencies missing, so it's coming. It's only 7,000 lines of code. In comparison to other developments, I think this is quite a small development, but the mathematics behind this is really hard. So nevertheless, it's like very densely packed. And this wouldn't have been possible without using several background libraries. So for example, we need quantum registers, probability theory, like in the last talk or the talk before. It was already said that Isabelle has a very great probability theory library. We also need Hilbert spaces, tensor products, Krauss maps, and a lot of mathematical stuff going on. And so many things were already formalized, and without this, this project would never have been possible. Yeah, I think that's about the conclusion. So we formalized the one-way to hiding theorem foundationally in Isabelle, and the next steps would be to find a more concrete bound. So the paper by Ambainis, Hamburg and Unruh also gives more concrete bounds, but that would involve a new proof. And we would like to have this connection between our formalization and the QRH tool. And obviously, if we could somehow work on our problems, that would also be nice. Thank you.
Thank you so much. Right. Do we have any questions?
Thank you. So for the second point of your next steps to incorporate it into the QRHL tool, what do you actually need to do? So what are the concrete steps needed?
So mostly it's this kind of parallel query stuff. That's like the main issue point, that we have to solve this problem. And then I think it's just showing like the equivalence, but that should be quite easy. But like this parallel query stuff is the main issue point.
Any other questions?
Hi, I would be interested, you said that you would allow non-terminating adversaries. So what is actually a non-terminating adversary? I mean, when will he find out the secret?
Yeah, so that's it's more like a mathematical generalization. But so what I intuitively would think is, okay, for example, if we have these kind of security games like the INCPA game, what happens if the adversary just doesn't answer? Like the adversary is required in the game to, for example, send you 2 messages or send the final bit to you. What if the adversary just doesn't do anything?
All right, let's thank Katharina again. Thank you.
Thank you.